Now I give the floor to Tomé Silva from SPAROS. As most of you know, SPAROS is the sponsor for the EAS student group from some time now. Tomé comes from University of Algarve also, where he did his PhD, and he will be giving us a practical application from tools that were born from knowledge and have been applied to the industry. So, Tomé.
Thanks, Nuno. As Nuno said, my presentation will be mostly talking about how we can take modeling tools and use them to address practical problems. I assume most of you I work in a company called SPAROS, which I assume most of you at least may have heard about. If you haven't, very briefly, I'll just tell you that it's an R&D company based in Portugal, and our areas of expertise are mainly around aquaculture and fish nutrition. And we have all sorts of activities. Good deal of them are related to producing custom feeds for R&D purposes, and also undertaking contract research trials for third parties. And besides that, we also develop and sell a range of commercial products targeting different species at different life stages. As for the subject of the presentation, it deals with models and modeling. So it's important to first clarify that throughout this presentation, whenever I mention a model, I'm talking about a mathematical model. And a mathematical model is just a formal quantitative description of a process. So for example, in this toy example, what we're saying here is that growth, which is a process, depends linearly on feed intake. And when we have a model, no matter how simple or how complex it is, we always have a response that we're interested, a response of a process that we're interested in predicting or studying. We also have a set of factors that influence this process, which we call the inputs, or the variables of the model. And then we have a set of parameters, or the constants in the model. I'm sure you've all seen a linear model before. What do we do with models? Of course, the most important thing we do with models is to run them. So if we know the parameters of the model, and if we have the inputs, we can somehow get an estimate of an output. And this is easy, just replace the values in the formula and calculate. On the other hand, first you have to know the parameters. So in order to do so, you need to basically solve an inverse problem, and this is more difficult in general. So what you need to do is to get a set of measure this process, the response of this process, under a different set of inputs, and use this information to try to find what are the best parameters, what are the parameters that reduce the prediction error. And this is where the mathematical modeling tools enter. And these mathematical modeling tools may seem scary, but most of the time it's something as simple as a linear regression, which I'm sure all of you have heard of. An important aspect of modeling and models in general has to do with model complexity. So for example, I could take the simple model that I've showed you, but I could make it more complicated. I could make growth depend linearly on feed intake and temperature, for example. And in such a case, because I'm introducing more factors, more inputs, more parameters, the model below is obviously more complex than the model above. And this is extremely important because there's a central principle in science, not just in modeling, but in science, which is the principle of parsimony, which means that if we have different theories or models about how something works, if they're equally accurate, we should always pick the simplest explanation, the simplest model, the simplest theory. And so the advantage of working with the formal quantitative models is that within mathematics, we have a very clear definition of what we mean by accurate and by complex. And this helps us to do things without having to resort to opinions. We can be more objective. And so let's say, an important aspect is to understand why models are good. And so far I've talked about two aspects in which models can be helpful. One of which is to help us understand or to explain processes. And this, again, we would use the principle of parsimony. The simplest model we can come up with that's accurate, it's probably not too far from reality. Another issue is that models allows us to summarize all the prior knowledge and data that we have about a process. So in this example that I gave you, for example, if we measure growth under different feed intakes and we estimate the parameters A and B, these parameters will basically encapsulate the information that we know about this process. In this case, A would be how much does the fish grow if it's not being fed, and B would be some sort of feed efficiency. For each gram feed intake that I provide to the fish, how will growth respond to that? But the main aspect of my presentation and what I'll be talking about next is basically how to take these models and make them useful in a practical way. And so to do so, you have to consider different steps. I will give you a simple example and go through all the steps so you can have an idea of how this thing works. So the first point is to identify a problem and to see how that problem is dealt with. So in the example, I will talk about the problem I identified, or the problem I will talk about is how can a fish farmer estimate the environmental impact of its operations? And often you don't have to identify a problem because problems tend to come to you instead. So this is an easy part of the easy step. As for identifying the methodologies that are used usually to face this problem, in this specific case, if a fish farmer wants to know the environmental impact of its operations, he can do two things. One is to directly measure them, but no one does this because this is extremely expensive, or not many people do this because this is expensive and difficult. On the other hand, a very widespread approach to do this is to use a mass budget approach. And to give you just a quick example, the underlying logic is that the amount of, in this case, nitrogen that we provide to fish, part of it will be retained in the body of the fish, which I'm calling N gain, and part of it will be excreted as waste, which I'm calling the N waste. So easily we can estimate the N waste simply by subtracting the total amount of nitrogen minus the amount that gets retained in the fish. This is how usually people measure this, or estimate waste. So the second step after you identify the problem and how people usually solve that problem is to assess limitations in how this problem is approached, or how the current approaches deal with the problem, and whether there are opportunities to improve these approaches. In this specific case, what we see is that while it's relatively easy to estimate the amount of nitrogen that we are providing to fish, because people know how much feed they're putting inside tanks or cages, and by law, the fish producers have to provide information on the amount of nitrogen in feeds. So it's relatively easy to estimate the amount of nitrogen in feeds. On the other hand, to estimate the amount of nitrogen that's being retained by fish, you need to not only know how much biomass was retained by fish, but also how much nitrogen there is in that biomass. And this, for a fish farmer, is far from trivial, because a fish farmer generally doesn't sample fish and measure their body composition, so for sure he will not know this off the top of his head. So we pass through the third point, which is try to understand better this issue, and the way to do that is to collect data. You have to either run trials or go to the literature, read papers and so on, and usually this is the step that takes most of the time. So in this case, for example, we wanted to solve this problem, so we went to the literature, we went through data from our own trials. This is data that was obtained under a wide range of environmental conditions. And for example, for sea bream, what we see here, this is a graph that shows how much nitrogen is in the body of the fish as a function of its body weight. You can see that this is almost perfectly linear. And this is data that comes from many different people under many different conditions. So it's quite surprising how clear this pattern is. You see that there's a linear relationship in general, though there are some outliers as well. So after we gathered data, we looked at the data, we saw if there's some outliers that we can, or that we should disregard, then we should try to model the data, to calibrate the model taking this data. In this specific case, we know that the parameter A should be 0. And this is because as the weight of the fish goes to 0, we expect the amount of nitrogen in the fish to also go to 0. So in this case, we could even further simplify the model before calibrating it. Then we have basically, well, we can approach this through different philosophies. The most straightforward approach would be to simply do a linear regression and you get the value for the B parameter. But the problem is that you get just a single estimate of for the nitrogen. For the environmental impact. Another approach would be to, for example, use quantile regression. And in this case, you actually get, for each body weight, you get the minimum and maximum amount of nitrogen. So it's a different way of doing it. This is just to show that there's different ways of doing it. So for example, taking the data set I showed you, you can fit a linear line, which gives something like this. Or you can fit two linear lines to try to cover all the range of possible values. You'll see here that some of the points are outside of the range. So usually you should go back to the data sets, to the data sources, and see why are these points strange? Is there a specific reason, or this is just normal biological variation? If it's just normal biological variation, we should keep. Otherwise, we should throw them away. In this case, to make things simple, I just kept them. So, well, on the left, the model, what it says is that basically fish nitrogen is a constant 2.8% of fish body weight. On this slightly more complicated model on the right, what we're saying is that fish nitrogen is between 2.7 and 2.9%. So it's straightforward as well. And as you know, once you have a model calibrated, then you can, for example, estimate the amount of nitrogen in a fish with 10 grams, either as a single value or as a range of values. In this case, we can say that a fish with 10 grams would have 0.20, or gilted silver in this case, with 10 grams would have 0.28 grams of nitrogen. Or if you want to give a range between 0.27 and 0.29. So going back to our question, what we see now is that we can overcome this limitation precisely because fish body nitrogen is extremely predictable if we know the fish body weight. So something that used to be not very easy for a fish farmer to do becomes easy. The last point is, okay, you have the model, everything is working okay, it's helpful, but the fish farmer is not going to read your paper to try to see a model and to try to apply a model. So you have to encapsulate this model and this knowledge as a tool that's practical and that a fish farmer can use. In a nutshell, what I'm saying is that the fish farmer should not have to understand the model in order to take advantage of the model. And at this level, there are several concerns one should have. First, the usefulness of the tool should be clear. If it's not clear why the tool is useful, no one's even going to try to use it. Then the inputs and the outputs and all the nomenclature used throughout the tool should be stated in terms that are familiar to fish farmers. We're not going to talk about nitrogen retention if that's not something that the fish farmer is used to think about. And finally, how to use the model should be pretty straightforward and, if possible, clearly documented. When it comes to this specific problem I mentioned, we actually went out and made a tool for it, taking into account these principles, and hopefully we were able to reach a good and usable tool. This tool is working not only for gilted cibrim, but for several species which have high importance in European aquaculture. So if you have interested in environmental impact, I would invite you to check it out. And so to sum up my presentation, the point I wanted to make across is that even extremely simple models can be very, very useful in a practical sense. But if we want them to be applicable to practical solutions, we have to take into account several points. One of them is that, of course, the model should address a practical problem, but also that we have to calibrate the model with enough data to cover all the practical solutions, so practical situations. So if you want a model that works at the 10 degrees or at 20 degrees, then we need to enter with data at a wide range of temperatures, for example. And finally, it's not enough to just make a model and calibrate the model and then publish it. If you want people to actually use the model, you have to make something that people can use straightforwardly and that follows what they expect and what they need. So that was it. And if you have any questions or something, I'll be happy to address them, or you can just send me an email instead.
Are there any questions for Tomé?
Sorry, I can't hear you.
The microphone's on the way.
Are there any other reporting sites for these farmers or anybody within the industry in Portugal? Like, the government mandates reports, you said I can feed that report. Is there anything else that they're supposed to report?
I'm not entirely aware of how things are dealt with in Portugal in terms of legislation and the actual application of legislation. But no doubt, throughout Europe, this is a concern that's growing, and authorities are increasingly putting strict limits on how much. You have to scale up your operations according to how much waste you're producing. So I didn't address your question because I really don't know how it works specifically in Portugal, but I'm sure that, for example, in Denmark, that's already being enforced. That's it.
Gotcha. Nope, that's great. Thank you.
Any more questions? No? Okay. Thank you, Tomé, for your presentation.
Cheers.